Hi, welcome to Math 256. This is Scott, and let's get started. Section 1.1. Differential equations, or diffEQs, and mathematical models. So first off, what is a differential equation? Well, it's an equation involving the derivative of an unknown function. For example, we might have something like dy dx is equal to 2xy squared. Now, the reason we might have something like this is that it's often easy to come up with some sort of a relationship that explains how a quantity is changing, but then difficult to figure out what the actual equation that determines the quantity is. So this could be a case where we know how y is changing with respect to x. It's changing like this, but we don't know what the actual formula for y is. Later on, we'll learn how to find this, but for now, it's a mystery. Now, what we could do, if given a specific formula for y, is check whether it actually verifies or whether it actually checks with this. And that is what it means to be a solution, is to satisfy this original equation. So solution is any function that satisfies the differential equation. But solutions to differential equations are like antiderivatives. They never come as just one, they come in a family. So solutions come in families, and they're parameterized by constants. These constants correspond with constants of integration that you may remember from Math 252 days. Now, when we want a specific solution to a specific differential equation, we need one more piece of information, or sometimes more than one more piece of information. We need what's called an initial value or initial constant, or initial condition. So, to find a specific solution, we can use an initial value, also known as an initial condition, to solve for the constant. So returning to that example from above, let's say that we were given, just out of thin air, a family of solutions, and we wanted to verify that it actually did the trick. So show that y equals, and now here, I'm just handing to you from on high a family of solutions. Later, you'll learn how to find this, but for now, it's just being given to you. Show that y equals 1 over c minus x squared is a family of solutions. To the same old differential equation dy dx equals 2xy squared. So what this is asking us to verify is that if we were to take this and take its derivative and put that in where dy dx is, and we were to square it and put that in where y squared is, everything would check out. The left side would equal the right side, and balance would be maintained throughout the universe. So let's give it a try. So what we are supposed to be verifying here is that the derivative of this thing, 1 over c minus x squared, we're supposed to be verifying whether or not this truly does equal 2xy squared. Well, here what we are talking about is really the same thing as c minus x squared to the negative 1. I've rewritten it this way because it'll be easier to take the derivative. You could do this using the quotient rule, but that's unnecessarily complicated when we can instead rewrite it this way and use the power rule and the chain rule. And this is supposed to come out equaling the same thing as 2x times 1 over c minus x squared, quantity squared. So now I've just substituted in for y the formula that we were given for y. All right, well now let's take the derivative here. So this is, again, a power rule and a chain rule. So the power rule says I should take that negative 1, bring it out to the front. So there it goes. But then according to the chain rule, I have to multiply by the derivative of the inside. Now c is a constant, so its derivative is 0. So when I multiply here, it's just going to be 0 and minus the derivative of x squared, which is just 2x. Now this, obviously when I take the derivative of this expression, the power rule says that I should subtract 1 from the power. Okay, back to work. So now this is supposed to come out equaling 2x 1 over c minus x squared squared. Now things are starting to look pretty good here. The negatives will cancel out. We ignore that 0, and sure enough, this questionable equals is not so questionable anymore. It's really a question of whether 2x over c minus x squared equals 2x 1 over c minus x squared, quantity squared. And sure enough, that is true. So it is indeed a family of solutions to the given system, or to the given differential equation. However, suppose we wanted to boil it down more specifically and find the value of the c. So if we wanted to pin down the family to a specific member of the family, we would need an additional piece of information. And when we're given a differential equation as well as an additional piece of information, that's called an initial value problem. So initial value problem. Usually abbreviated IVP. This is a differential equation and an initial condition, or an initial value. So, as an example, let's take, once again, our old friend dy dx equals 2xy squared, and we will specifically stipulate that we are looking for the solution where y of 0, so in other words, plug in 0 for x, and y should equal 1/2. So what this means is that once we have the family of solutions, we're going to use this to find the value of c that makes this work. So here we go. So we already know from our previous work that the family of solutions in question here is 1 over c minus x squared, and then we are going to be plugging in we're going to be plugging in 0 for x, and that's going to equal 1/2. So we have 1 over c equals 1/2. In other words, c has to equal 2. So then what that means is that y as a function of x, we can write it this way or just y, either way, is equal to 1 over 2 minus x squared. So there is our solution to the initial condition. Now what we have here is a differential equation that involves just the first derivative of y. But there's no law that says it has to stay that way. Note: differential equations can involve higher derivatives. By which I mean second, third derivatives of the function y. The order of the derivative is the order of the differential equation. So an example of a second order would be something along the lines of this. Could have x squared times y double prime, and here, as usual, when I have x's and y's floating around in the same equation, I'm assuming that y is a function of x and that the derivatives of y are the derivatives of y with respect to x. So we could have something like x squared y double prime plus 3x y prime plus y, so in other words, so the zeroth derivative of y, and that all could equal 0. So here's an equation. It involves not just the derivative of y prime, but the second derivative of y double prime. Now, if I wanted to verify a proposed solution to this, I would have to take its derivative a couple times over and deploy all the derivatives in their appropriate spots and verify that it actually all worked out. Now, here is a solution that we might want to verify. And a solution that we might have here is y is equal to x to the negative 1 times the natural log of x plus 4 times x to the negative 1. And as a note for domain reasons, because the natural log is only defined when x is positive, we might have as a special specification here that x has to be greater than 0. So to verify this, what we would need to do is take the derivative and the second derivative of the y, and confirm that it actually fits the bill. So once again, the y in question here was equal to x to the negative 1 natural log x plus 4 x to the negative 1. So if that's the function that we're claiming is the solution to this particular differential equation, or a solution, I should say, then what that means is if we take the derivative, we take the second derivative, we put everything where it goes, we should get something that checks out. So let's start by taking the derivative here. Now, because what we have is a product, we're going to have to use the product rule. And x to the negative 1, the derivative of that is going to be negative x to the negative 2, and we leave the second factor alone, so it's going to be ln x. And now, so this is playing the role of what we usually call a u or an f. This is playing the role of what we usually call a v or a g. And so now what we're going to do is we're going to leave the first one alone and take the derivative of the second one. So leaving the first one alone, we have x to the negative 1, and then times the derivative of natural log, which you may recall is equal to 1 over x, which is in fact the same thing as x to the negative 1, but just because it's more familiar to write it this way, I'll write it as 1 over x. And then plus the derivative of the second term here, so that's going to be, down comes a negative 1, which is going to make it negative 4x to the negative 2. Alright, clean this up a little bit, and we're going to have negative x to the negative 2 ln x. And then if we look at this part, that's going to actually make an x to the negative 2 as well. And here we have minus an x to the negative 2. So we have an x to the negative 2 minus 4x to the negative 2. So it's going to make minus 3x to the negative 2. So there's where things stand as of right now. We take the derivative one more time to get the second derivative, and here we go. So once again, we're going to need to use the product rule. So we have two factors here. The first factor, we're going to pull down the exponent, and that's going to give us a positive 2, and then that's going to become an exponent of negative 3. The exponent gets dropped by 1. And then we leave the second factor alone for the time being. And now we leave the first factor alone, negative x to the negative 2, and we take the derivative of the second factor, the natural log, which will be 1 over x. Alright, and then coming next here, we have plus now, so the negative 2 comes down to make a positive, and a 6, and then it's going to be x to the negative 3rd. And now a little bit of cleanup, that's going to be the same thing as x to the negative 3rd, so minus x to the negative 3rd plus 6x to the negative 3rd. So combining like terms, cleaning up, we have y double prime is equal to 2x to the negative 3rd ln x, and then altogether it's going to be plus a total of 5 x to the negative 3rd. Alright, so there's y prime, and there's y double prime. Those are the three characters that are going to be put into action in our little differential equation. And to verify that it all checks out, we need x squared times y double prime. So it's going to be 2x to the negative 3rd ln x plus 5x to the negative 3rd. So this is the y double prime there, plus 3x times, now it's going to be just y prime, so it's going to be negative x to the negative 2 ln x minus 3x to the negative 2, and then plus, that's just y prime, and then plus just regular y. So that's going to be now x to the negative 1 ln x plus 4x to the negative 1, and that whole equation is supposed to come out equaling the same thing as the right-hand side of the differential equation, which was just 0. So we have the three pieces in play here. And we will do the necessary amount of algebraic simplification and see what we get. So those are the three y pieces. So the x squared, we distribute that throughout, and we have 2x to the negative 1 ln x. We have plus 5x to the negative 1. For the next part over here, we have minus 3x to the negative 1 ln x. We have minus 9x to the negative 1. We have plus x to the negative 1 ln x plus 4x to the negative 1, which is supposed to all end up equaling 0, so hopefully we're going to see a whole lot of canceling here. And if we look at the pieces in play, we have 2 x to the negative 1 ln x, minus 3 x to the negative 1 ln x, plus 1 x to the negative 1 ln x. So those three things all cancel each other out. And similarly, on the x to the negative 1 terms, we have plus 5, minus 9, plus 4. Sure enough, those all cancel each other out as well. And we have 0, which is supposed to equal, on the other side, 0. Checks out. So that's what it can look like if we have an equation of higher order, by which we mean a higher derivative. Now, let's look at some of the different kinds of differential equations. All right, so we've already seen a first order differential equation. That was the one that we started with, and the important thing about that is that it has no more than the first derivative. So we could have something like y prime, which is equal to something that involves just x and y. So we write that by just saying it's a function of x comma y. So meaning whatever this expression is, it's just some scrambled up combination of x's and y's, but no derivatives. Now, ordinary differential equations, which is going to be the focus of this class, so for ordinary differential equations, or ODEs, what we are talking about are functions that have only ever one input variable. So here we are only ever talking about a single independent variable. There's only one independent variable. So the derivatives that we're talking about are ordinary derivatives. They are not partial derivatives, but just regular good old-fashioned derivatives. So the derivatives are not partial. So that's the important thing about that. Now, that's what this class is going to be dealing with. However, in more advanced classes, such as you might see later on in your education, you can also explore what are called partial differential equations. So partial differential equations, or PDEs, PDEs. These, which we are not going to be focusing on here, let's just start over. PDEs. So these, which is not going to be our focus here, these are frequently encountered in all sorts of engineering and physics contexts, and they do involve partial derivatives. So these involve partial derivatives. Now, those of you who have been around the block a little bit, have taken, for example, Math 254 vector calculus, will have seen a little bit of this. An example of something that looks like this would be what's called the heat equation. And here, because we're talking about a partial derivative, we write the derivative not using a standard d, but instead the script delta. We could have the derivative, the partial derivative of u with respect to t is equal to k times the second partial derivative of u with respect to x. Now, it's not really important for us to dig too much into the details of this. However, this is a thing that is the subject of a great deal of study in classes that are devoted to partial differential equations. It's not our business though, so we are going to just move on with our lives and look at some specific ordinary differential equations. So some of the specific examples of ordinary differential equations that we can explore come to us, for example, from physics. So here are some classic examples of first order ordinary differential equations. So that's our game right now. First order ordinary differential equations. And we can start with something like Newton's law of cooling. Newton's law of cooling. Also Newton's law of heating, but usually phrased as Newton's law of cooling. So the way this is typically worded is something along the lines of the following. The rate of change of the temperature of a body is proportional to the difference between the temperature of the body and its surroundings. Okay, so that's a phrase that describes it, and you can make sense out of it, but we need to figure out a way to mathematize it, turn it into the system of hieroglyphics that we know and love, that involve derivatives and things like that. So let's try to translate it. Basically, phrase by phrase, the rate of change of the temperature of a body. So we'll say the rate of change, so capital T for temperature, lowercase t for time. So rate of change would be the derivative. And then it says, is proportional to the difference between the temperature of the body and its surroundings. Now, proportional, we will frequently use a letter such as K for a constant of proportionality, and the difference between its temperature, so again T, and then the ambient temperature, or the temperature of its surroundings, we can use an A. Now, I left some space in here because whenever we have a constant of this sort, we by default would want to arrange the formula so that the constant in question is positive. Now let's think about this particular situation. We're talking about the rate of change of the temperature with respect to time. Now, if the body that we're talking about starts off being warmer than the surroundings, then its temperature is going to be going down. So if this difference is positive, the rate of change should be negative. Conversely, if the body in question is cooler than the temperature around it, it'll be warming up. So if this temperature is less than this, so in other words, if this difference is negative, the temperature will be increasing, so this should become a positive amount. So we will put a negative here so that the constant K can be assumed to be positive, and this will indicate that the temperature is changing in the reverse direction of this difference. So this would be the differential equations version of Newton's law of cooling. Now again, we can formulate the differential equation, but we can't actually solve it at this point with the tools that we have, although it won't be long before we learn how to do it. But we just want to look at some cases of how we can formulate things. All right, here's another example, also from physics. This is Torricelli's law. And what it has to do with is the rate at which water drains out of a tank. And in particular, the rate of change of the volume of water in a draining tank is proportional to the square root of the depth, which we can say is y, of the remaining water. So this has to do basically with the pressure of the water that hasn't drained pushing down on the water and causing it to spout out at a rate that will be getting less and less as the depth gets less and less. And the way it'll be getting less and less is as the square root. But the important thing here is to just take this as a law of physics and try to translate it into its mathematical form. So now we're talking about the rate of change of the volume. So it's going to be the rate of the change of volume with respect to time, and it is proportional to the square root of the depth. So again, we'll use K as a constant of proportionality. But again, we are going to, by default, reserve a positive value for K whenever we can, so that way anybody looking at the formula will know which direction it's going. So let's think about this. As the depth is greater, as the depth goes from greater to lower, the rate of change of the volume is going to be getting less and less. And it's because no, actually, scratch that. The way I should word this is the volume is always decreasing, and because it's draining, and so it's going to be negative K square root of y. All right, so that's another example. And now the last example for right now, last example of this section, the last part of the first of these lectures is the example of the case of uninhibited growth of a population. So this is uninhibited, uninhibited growth. So uninhibited growth. So here, what we would be talking about is a population of animals, let's say, that are growing without any kind of constraint. So what's happening is that the rate of change of the population with respect to time is going to be just increasing at a rate that is proportional to what the population currently is. Now this actually you have already seen before, but what you called it then was exponential growth. And what we actually know from previous studies in Math 111, for example, is that the formula that describes this has this general form. So the population is equal to some constant, and this is the same c as we saw before. It's the parameter for this family of functions. It's going to be that same parameter times e to the kt. And then, based on whatever information is given to us, we can solve for the c, which, again, those of you who have a memory for Math 111 stuff, the c here is exactly in the spot for what we used to call the initial population, or the initial value. So when we were to plug in a value of 0 for t in this case, what we would end up with is actually getting the value of c, which just is the initial population. But anyway, enough of that. Enough of it for now. Let's go ahead and call it a lesson. Join me next time for section 1.2. Thank you.